All right, welcome everyone. Uh, so this is going to be day 2 of your Newton's second law lab. Goals for today is that you can determine the graphical relationship between the acceleration and mass of the system. We want you to be able to linearize an acceleration versus mass plot. So we'll talk more about what that means in a little bit here. You're going to take notes on graphing acceleration versus mass. And then you're going to practice linearizing an acceleration versus mass plot. And then you're going to linearize your acceleration versus mass plot from the data collection assignment. So the first assignment from this lab. So in the first part of the lab, you plotted your acceleration against the mass of the system. And when you did this, you probably noticed that the graph was not linear, right? It had this sort of like weird curve. It was probably tough to get any of the values to have a good curve fit. There's one that probably fitted pretty good, but it's not one that we've used before, and it's not one that's going to be useful for determining the relationship. So in order to determine the relationship between the acceleration and mass, we must linearize our graphs. So what does that mean? That means make them so that the data plots in a straight line. And we can do this using Newton's second law. Okay, so let's kind of jump into it. Let's first review our force triangle. Remember, we have F on top, M and A on bottom, and we get 3 equations out of that. So F equals M times A, M equals F divided by A, and A equals F divided by M. So go ahead and write down those equations. And so then this is kind of what your acceleration versus mass plot should have looked like. I, of course, used different data here, so the numbers work out to be a little bit different. But this is kind of what your plot should look like, right? It should have the data points should make a curve, and then when you try to plot a straight line on it, it doesn't really go through any of the data points because the data is curved and the line is straight. And so we can see that you can get a curve fit to fit the data. I had to use what's called a power series to do that. And so power series, the math is a little bit complicated. And it's not really all that useful for determining the relationship. So that's why we're not going to actually have a good fit with this data. Instead, we're going to linearize the data and then use that to determine the relationship. So going back to this graph, if we take a look at the slope, so remember slope is rise over run. Well, in this case, our rise is our acceleration because that's on the y-axis, and our run is our mass, that's on the x-axis. So acceleration over mass. Well, if we jump to our force triangle, we can see that the one where we have acceleration and mass on the same time, on the same side, they're multiplying by each other. Here they're dividing acceleration divided by mass. Well, if you look at all the relationships, there is no relationship in Newton's second law where you have acceleration divided by mass. The only operation you can do with mass and acceleration and to get a meaningful relationship is to actually multiply them together. So what does this slope of this line mean? Well, nothing really, right? We don't actually know what this slope means because acceleration divided by mass, that's not a relationship that we're familiar with. Sorry about that, the loudspeaker came on at school here. So yeah, the acceleration over the mass, we don't really know what that means, and it really doesn't mean anything. It doesn't have any real value for us. So what we're going to actually do is linearize our math data. And so the way that, or our mass data, excuse me. And so the way we're going to do that is we're actually going to take our mass and we're going to take 1 divided by each of our mass data points. So like for our first data point here, we're going to do 1 divided by 0.1. That equals 10, so then our mass data point is 10. For our second data point, I'm going to take this 0.15, I'm going to go 1 divided by 0.15. that equals 6.7, so I'm going to put in for 6.7. You guys calculate the rest of these, and then once you finish calculating them, you can put them in on the next page here, so you can just copy them over if you want to. And then what we're going to actually do is plot 1 over the mass versus the acceleration. Or actually the acceleration versus 1 over the mass, I should say. And so you can see on this graph I've got acceleration on the y-axis and 1 over mass on the x-axis. And when that happens, those data points will make a straight line. And so now we can find the slope of that line, and this slope is actually going to have some meaning. This graph right here, the equation ends up looking like this: y equals 0.245, and then these are the units: meters per second on the y-axis, 1 over kilograms on the x-axis. So it's meters per second divided by 1 over kilograms times x, and then plus 0 meters per second. So if we translate that into substitute in the variables from the experiment, we're going to get A equals 0.245 meters per second divided by 1 over kilograms, and then times our x variable is 1 over mass, right? We can see that down on the axis here, so I'm putting that in as 1 over m. Right, and then I've just ignored the 0 because anything plus 0 is just itself, right? So I'm just including the front part of this equation. So this is my formula. Now let's kind of find out what it means. Well, in this case, sorry about that, folks. Lost my train of thought for a second there. So what we're going to kind of show is that this slope right here is the force on the next slide. And so we're going to do a little proof to show that. So if we look back at this slide, we can see, we can tell that whatever this value is, it's the acceleration over 1 over the mass. So we're going to say this is acceleration over 1 over mass. Now, I'm kind of giving away the end here. We're going to show that this is equal to force. And we're going to do that using Newton's second law. So acceleration over 1 over mass. Well, if we write that as a fraction, it'll look kind of like this. Acceleration is going to become acceleration over 1, and then I'm going to write this more vertically, so 1 over mass. Well, remember, when you divide two fractions, that's the same thing as multiplying by the reciprocal of the second fraction. So this is just going to turn into a over 1 times m over 1. Right? I just flipped the second fraction here. Okay, and so then, well, really, since they're both over 1, this is just going to be the same thing as saying F equals A times m, or F equals m times A. F equals net force, and so that's because we can see F equals m times A. That's our equation from the force triangle. So really what our slope means is the net force. That's the meaning of our slope, is F equals net force. Okay, so let's simplify the units of the slope. So remember, slope, sometimes that's written as m. That's just your rise over your run. So in this case, our units for our slope were meters per second over 1 over kilograms. So we're going to kind of do the same thing. We're going to write this as fractions. So our slope is going to be meters per second over 1. So I took the top part of this equation and I put it over 1. And then I'm dividing by the bottom part, 1 over kilograms. Again, we're going to take the reciprocal of this fraction. We're going to take the reciprocal of 1 over kilograms. So that's going to become kilograms over 1. So then when I multiply those together, we're going to end up with our slope being meters per second times kilograms. I'm going to write it the other way, kilograms times meters per second. Remember that that is the same thing as a Newton. A Newton is a kilogram times meters per second. So really, our slope of our equation is in newtons, and that should make sense because we showed on the previous slide that our slope is really just the net force, right? And force is measured in newtons. So I'm going to rewrite the equation. I'm going to simplify those units. The equation is going to become A equals 0.245 newtons times 1 over meters. Okay, and so then what you're going to do from here is you're going to take your data from day 1, and so then what you're going to do with that data is you're going to put in your mass data, you're going to put in your acceleration data, and then you're going to linearize the mass data. So you're going to take each data point for mass and take 1 divided by that data point, and you're going to write that in right here. Do that all the way down, and then what you're going to do is put the assignment, or put that data, the 1 over, you're going to put the 1 over mass data and the acceleration data into pivot, and then you'll make it into a graph. You'll put a linear best fit line on that graph, and then you'll include a screenshot of your graph and your best fit information below. Don't forget to include the best fit information. A lot of you are forgetting to do that. That's going to be important. After that, you're going to write the equation with the variables from this experiment down below, and you're going to simplify the units for the slope, so just like I did in the examples. And then you're going to tell me what the meaning of the slope is with respect to the experiment. You're going to write your answer as a complete sentence below. If you have any questions, let me know. We are going to go over this as a class, but give that a try. Let me know if you have any questions.